So let's continue about law of refraction. So we had a diagram here, right? Like this. And this is the normal, there is incident light, this is making angle theta I, and this light got reflected, once it got to the boundary, and this angle was theta R. This medium has a refractive index NR, and this has NI. And we looked at NI sine theta I equal to NR sine theta R. Okay, so this is called Snell's law. Now I'm going to make another diagram for the same case. It does. So the light ray doesn't have to go from this one. It could also come from this medium and come out. Okay. So for example, that case would be here, right? So if we let this light come down here, so it comes here, and then if we draw another normal here, right? What happens? It is going to bend, right? Now it's going to bend in different way. It won't go in the same direction, so it is going to bend like this, right? Okay, now it will bend away like this if refractive index of this medium is lower than the refractive index of this medium, okay, where it is coming from. So now let's look at another case here. Okay, so I'm going to draw let's look at it for total internal reflection. Okay, so this time reflection. This was refraction, this is reflection. Total internal reflection, or we can also call TIR. Okay. Now let's draw a diagram here. Oops, maybe a little bit further down. Like this, right? Okay, so I have a normal drawn here. Let's say this is our now NI, this is our NR, okay? We can change, we can have a, so this this diagram is now, it's, we could say, let's forget about this one and just let's look at this one. So now I have a ray light, this is incident, let's call this angle as again theta I, incident. Now it's going from in, okay, from this medium with the refractive index Ni. Once it reaches here, what happens is some of the light, they get, once it gets to the boundary, some of the light would get like transmitted, okay. So basically transmitted meaning really they go like that, or they get refracted here, right? Once they hit the boundary, some of them would go here. So this would be, theta refraction, right? But some of the light, depending upon this angle, some of this, and the refractive index of this material, some of the light would probably go even like this, along this surface, or some of the light actually even, if we have this light incident, some of the ray may even come back like this, okay? So this condition here, when this light, this refracted ray basically, it goes along the interface, this is called condition for critical angle, okay? So using this equation here, Snell's law, Ni sine theta, critical angle as a C, we call critical angle theta C as a critical angle, equal to NR sine, if this is going along the boundary, along this interface, what's the angle with respect to the normal? So the angle with respect to normal would be this is 90 degree, right? So 90 degree we have. So that would be sine 90 degree, okay? So we know sine 90 is 1, right? So sine theta C is NR divided by NI. sine 90 degrees 1. So we can really find the critical angle theta c equal to sine inverse of nr divided by ni. Okay, so this equation here, this gives us how to find critical angle. Okay, so the critical condition for critical angle is when the incident light touches this boundary, right? When the light is traveling from one medium to another, and the refracted ray, it travels along the interface, along the plane of the interface, making 90-degree angle with respect to normal, then that angle will give us the critical angle. So critical angle is not the 90 degree, but critical angle will be this, okay, theta I. So this critical angle is, there is a specific critical angle for different material, okay, so different material has a, they have their specific value of critical angle. Okay, now this theta c, right? So now another thing also is this. Now when this this theta incident angle becomes a critical angle, then the light is not going to pass to the other medium. It's gonna come back to the medium it was traveling through. Okay, so all the light is gonna come back to this medium, meaning really this angle, right? If the angle of incidence is greater than this critical angle, then the light enter from this medium is going to reflect back to this medium. So this is a TIR, total internal reflection. Okay, so this guy here. So when angle of incident theta I is greater than critical angle theta C, total internal reflection takes place. Okay, so all the light is going to come back to the same medium, reflect back. Okay, so this is the case for a total internal reflection. Okay, so let's do one example. What is the angle for total internal reflection for light going from water to air? Okay, so assume, or not assume, really use n of refractive index of water equal to, let me check the value, refractive index of air is just 1. Okay, refractive index for water, let's see. This is 1.33. Okay, refractive index for water is 1.33. So please try working on this. Okay guys, so I'm gonna erase this here. Okay, so here, what's the angle for total internal reflection? Basically we're asked what's the critical angle, right? The angle bigger than the critical angle would be the angle for total internal reflection. So let's say theta c equal to what? Light going from water to air, so in water is 1.33 and air is 1. Okay, so now we know from condition for total internal reflection, right? Or really calculation of us, so we know critical angle is given as what? Theta c is given as sine inverse of what? NR by NI, right? So here, what would be our NI? Where the light is going from, that would be the incident, right? Medium through which light is incident. So it is going from water, okay? So our refractive index would be of incidence has to do with the refractive index of water. It is going from water to air, okay? So here we can just write sine inverse of our ray of light is going from water to air, so it has to, the R would in the index of refraction here would be NR would be our air, okay? So 1 divided by NI would be water, right? So okay, maybe let me write this one more step so you guys can see this. And refractive index, that would be NA, air, divided by N, water, okay? You have to be careful, you cannot have the other way, okay? Otherwise you won't get the value for here, even calculation. So sine inverse of refractive index of air is 1, refractive index of water is 1.33, and if you do the calculation here, what do you get? Let's look at the value I got. So it turned out to be 0.85 degree, okay? That's it. So this is the critical angle. So any angle greater than this angle, if the light is incident at angle greater than this critical angle, then the total internal reflection will occur. So you want to write here TIR occurs if theta I is greater than this angle of theta c, okay, like that. So far we talk about the property of light, right? Light reflects, right? Light refracts. There is also another property called dispersion of light. Dispersion. So here it is like this. If we have if we shine a ray of light in a prism, then from the other side of the prism we get a rainbow, guys. Have you seen natural prism? Have you seen rainbow in the sky? That's what I mean to say when I said natural prism. So this has to do with this phenomena is called dispersion of light. So it turns out that actually Newton did, contributed about this dispersion of light. What he concluded was like, white light is composed of 7 different colors or 7 different colors of light. Okay, so let's see if we have this. Let's say, I'm going to make the same diagram like that there. Okay, so it's going to incident here, and then if we have it in a certain way, and then after, once it enters here, if it's going like this parallel, it's not going to refract here inside, right? Because it's going parallel to the base. Okay, now when it exits, so this is a white color, white light. When it exits, it turns out that it exits like a rainbow color. So rainbow has how many colors do you know? Okay, sorry. Let me start making it from the beginning. Yes. I have that dot here, guys. So it turns out I couldn't draw more, but basically 7 colors. Okay, so you would get like this, something like this: violet, indigo, red, or not red yet. I'm gonna write down here. So basically, I have only 4 here, but actually it does 7, okay? Because I couldn't fit in here, so I'm putting this like dot dot dot, means there are more things in between. Okay, so we have a violet color, we have indigo, we get blue, we get green, we get yellow, we get orange, we get red, and always the violet color bend most, okay, and the red color bend least. So here also see, the violet color, it has bend, it bend most, and then the red color is just a little bit of bending. Okay, so why does that happen? Why do you think this happens? So so different color, they are associated with different wavelength, right? Okay, so they have a different wavelength, and then when they go through this material, this material has a different refractive index, right? So because each of the since the white light is composed of a different 7 different color, when they refract, because of their different value of a refractive index, I mean different value of wavelength, they emerge as a rainbow. Okay, so even though it's a white light, we could get a rainbow here. Now, do you think it is possible to get a rainbow, I mean white light again? If, if 2 plus 2 equal to 4, 4 should also give us 2 plus 2, right? That's the logic, right? So, yes, in principle, it should do that. And then, so if we apply some filter here, then we can combine all of this light and then again actually get the white light. Here, Newton actually tried doing that, and then he also obtained the white light when he put a filter here. Okay, so this is another phenomena, manifestation of light. Now, so rainbow, right? see, that is also rainbow. It is also rainbow. Really, both are dispersion, right? Like the spectrum you get from prism and the rainbow spectrum you get. Like this is a natural spectrum you get. Both of those are due to dispersion. It turns out that we see the dispersion outside because when the sunlight hits the water molecule, then when the light enters inside the water molecule, the light, the white color and the violet color, they refract at a different angle. It turns out they refract at a 42 degree. So when they refract at different angle, that's how we end up seeing seeing this rainbow. So actually inside the molecule, water molecule, this is a water molecule here, white light enters, and then it goes through series of refraction here, and when it turns out, you see the violet color is always bend most and the red color bends least. Okay, and